You can say it.
Physical science stuff.
Okay, we're talking about, it is physical science time. We're talking about static electricity. So write that down, please. You remember, we talked about the 4 fundamental forces of the universe. Well, that is, I talked about it, and you guys watched a video about it, of me doing it. But the 4 fundamental forces of the universe, this continually comes up throughout the year. The one we talked about at the time, do you remember this at all? What was the one we talked about? Gravity. Gravity was the one we've already talked about. What were the other 3? Does anyone remember? Give me one more. So I'm going to make a little aside here. 4 fundamental forces of the universe. We had gravity. That's way down at the bottom. It's the weakest. Remember, it's both the weakest and, because it's the weakest, it's also the... Are you saying...
Like it has the longest range.
Longest range. Yeah, acts over the longest ranges. What was that? Okay, yeah, so the gravity was the weakest but had the longest range, has the longest range.
Electricity.
Okay, yeah, the electromagnetic force was number 2. The electromagnetic force, that's the one we're talking about today. And then the other 2 we don't very often talk about. We will talk about both in this class, but they're not something that we encounter on our daily life. Or we do, but we don't really think about it. They're both about the strong nuclear force.
Radioactivity.
And the weak nuclear force.
Oh.
The weak nuclear force has to do with some kinds of nuclear radiation, as Wade points out. But so these are the 4 fundamental forces of the universe. You can remember this will be on this test. You can remember this by the acronym SEWG. That's how I remember it. SEWG. Yeah. So in order from strongest to weakest, and in reverse order of shortest range to longest range, they are strong nuclear force, electromagnetic force, the weak nuclear force, and gravity. Gravity is orders of magnitude, so thousands of times weaker than the other 3. Yes.
So is it the other way with the distance?
Yes, it's the other way with the range over which they act. They all are technically universal. Like if there were only 2, the strong nuclear force relates how protons are attracted to each other, and so are neutrons. If there were only 2 protons in the universe, they would eventually be attracted to each other because of the strong nuclear force. But in general, this drops off extremely quickly, like on the order of smaller than an atom, whereas this acts over extremely long distances, light years at times. This is what gives galaxies that are light years across their shape. So gravity works over the longest range. Okay, so anyway, today we're talking about the electromagnetic force. So obviously, the electromagnetic force is made out of 2 what we consider daily, like our normally encountered forces, which are probably what? Electromagnetic force is made out of what other 2 forces, probably? Electricity and, yeah, the magnetic force. So in this case, we're talking about static electricity. And this is as opposed to, we just talked about this, what's the other kind of electricity we commonly talk about? Current electricity. So static electricity as opposed to current electricity. And in this case, I've put this arrow here because it is the electromagnetic force. But static electricity occurs when electrical charge accumulates on an object, usually on the surface. When we're talking about electrical charge, there are 2 polarities of electrical charge. You know what they are. What do we call them?
North and south.
Positive and negative. They're north and south for magnetism, but they're positive and negative for electricity. So positive or negative. And I shouldn't have to tell you this, but like charges, if we have 2 positive charges, what are they going to do?
They're going to
repel. They're going to repel. If I have opposite charges, positive and negative, they're going to attract. So, yes. Occurs when electrical charge accumulates on an object. And so we can say over here, like charges do what? Repel. Opposite charges
Attract.
Right, this is true in your cute little high school romantic relationships too, right? Opposites attract. Opposites attract. My wife and I are very, not in all ways, but in many ways we are opposite people, and that's one of the things that attracts us to each other, right? It's the same when you get your little girlfriend or little boyfriend or whatever, right? Opposites attract. how does it work romantically? That's not within the realm of this class. We're going to talk about how it works electronically or electrically. That is within the realm of this class. But you can figure that out on your own, Carter. Wait, don't do it in here, please. What?
Does it really actually matter if you have a positive?
Okay, please. Let's all try to be a little bit quieter. Wade, what was your question?
Does it actually matter if you have a negative wire where a positive wire should be, and a negative wire where
Okay,
a positive
no, so the wires themselves, as a custom, like you're talking about how, like we generally use a black wire to indicate negative charge and a red wire to indicate positive charge. Those are arbitrary, right? They're there so that you can remember, I have this one hooked up to the positive end of this battery, for instance. But no, the wire itself, all it does, as we'll find, is conduct charge. Sorry, we now are going to write this thing down. We're going to have another conservation of, can you guess what it is this time? Electric charge. Conservation of electric charge. And we can even call it the what of conservation of electric charge, probably. Law of conservation of electric charge. So now we have quite a few laws of conservation, right? What were they? Let's name a couple more.
Law of conservation of
Energy.
Law of
Charge.
Matter or mass.
Gravity.
Charge. And then we had another one called momentum. There's also one for angular momentum. But other than that, this is basically all of them. So, law of conservation of electric charge. And what this means is that if one object loses, for instance, a negative charge, another object must gain that same negative charge. So the total charge in the universe is always the same, right? If we add up all the positive charges in the universe and all the negative charges, we're going to get the same number from second one of the universe until now, right? The total amount of charge is the same. When an object has neither, sorry, give me a second, Carter. When an object has neither a positive nor a negative charge altogether, what do we call that? Neutral. And is an object neutral usually because it has no charge at all? No, it's usually, in the same way that we had balanced and unbalanced forces, at the time we said that forces were usually, there was no net force generally because all the forces were balanced, not because it had no forces acting on it. In the same way, an object that is neutral is generally has balanced charges. So like, here's you, with your long old legs. There you go. You are made of particles. You know? Did you know that? You're made of particles. Do you know what the particles are named? Yeah, you're made of atoms, and the atoms themselves, do you know what they're made out of? Protons, neutrons, and electrons. So your whole body is made out of protons that have a positive charge. Let's see, that's 7. And electrons that have a negative charge. And you have to have, if you're neutral, you have as many, at any given moment, electrons in you as you do protons, right? So your total charge, what we sometimes say your net charge, here is what? Equal to 0. Yeah, and we say no net charge, or we sometimes call this neutral. So all objects are made of charged particles, but not all objects themselves have a charge. Is that clear to you?
Yes.
So how can we impart a static charge on an object? You know this. How do you?
Rubbing.
Yeah, generally that. So sometimes a static charge can be given to an object by friction. Which of these do you think? Which one has the negative charge? Which subatomic particle?
Electrons.
Electrons. So electrons are negative.
And neutrons.
Electrons are negative. Protons are positive. What charge do neutrons have?
It's
No charge. No charge. So neutrons, no charge.
Or neutral.
Do you have a question?
Actually, kind of.
Let's hear it.
Can we make ourselves like magnetically things?
No, so magnetism and electricity, they're the same force. It's the electromagnetic force that governs both, but they don't, and they are related. But having something be positively charged is not the same thing as having a magnetic north pole, for instance, right? They're not directly related in that way.
So we can't have like magnetic powers?
Not generally, no. But if you have a static charge, you also have a magnetic charge. And we're going to get to that in the next chapter. But for now, you clear on this, though? So if we were to give, when have you ever had a static charge? And you probably do a slight one now. But have you ever had a static charge, and how do you know?
It shocks you.
Yeah.
Yeah.
When I turn my light switch on in my bedroom.
Yeah, maybe your hair stands on end. Maybe you get shocked by something. when something shocks another thing, that little shock is the discharge of static electricity. Hold on, wait, I have to get through this first. Okay, ask your question quickly. Quickly.
So is the static electricity the same as whenever like the train goes by and like whenever people say do not touch the rail after train goes by?
Yes, probably that's because of the static charge. Yeah. So a static charge can be imparted on an object generally by its rubbing.
Oh.
And of these three subatomic particles, which one of them is the easiest to move? Do you think?
Electrons.
Electrons. In fact, we call the flow of electrons. That's what electricity is. The flow of electrons. The flow of electrons. That's electricity. So when we're talking about electricity coming, I mean, it doesn't really work exactly, but when we say that electricity has come out of the wall outlet, right? That is the electrons flowing from whatever's inside the wall outlet out to your toaster or your hair dryer or whatever, your phone charger, yeah. So the flow of electrons is electricity. And so generally, when one object rubs on another, either electrons are being removed from one of those and passed on. Well, that's always the case. Electrons are always being moved from one to another. So I have a little... You can see it. I think you can see it pretty well, actually. Let's get rid of this right away. Okay, so I have this little thing here.
Oh, then you
I have a little rod. Yeah. Oh, I need a Kleenex. Roman, grab me a Kleenex and like tear the plies apart. Do you know what I mean by that? Like unply it. No, like it's two plies, so like separate the two plies.
Oh,
Yeah. Okay, so I got this little rod here. This is plastic of some kind. I think it's PVC. This is sheep's wool. Came from a real dead sheep. Yeah. So I'm just gonna. Can you hear that?
Yeah.
We can hear it rubbing, but can you hear the little crackles in it? So what it's doing is that sound is electrons. Thank you. That sound is electrons moving. In this case, almost certainly from the wool of the sheep onto the PVC. So the first thing we're gonna do is I have these little. I'm trying to make it so both you can see it and the camera can see it. But okay, so I've just torn up this one ply of tissue paper. What charge do the tissue papers have right now?
Negative.
Try again.
Positive.
No charge. No charge.
Wait.
No charge. They're just hanging out.
It's 15 feet wide.
Okay. They're just.
Can you move that white box a little bit, please?
This one.
Yep. Thank you.
So I have this. I'm charging this, right? Let me hold on. Let me show this to you. Here's another one. It's the same exact rod, right? Oh, I gave it a charge on accident. But watch this. Good. Whoop. Look at that. Can you see it on the camera, I wonder? Come here, little guy.
Oh.
False.
Oh.
Catch it.
Give it more charge. I wish the whiteboard were black.
So.
Or I wish I had little black tissue papers. Ooh, let's put it in front of my body.
I have a question.
No, I'm having fun.
Try to get, knock it. Try to catch it whenever it falls.
No. Okay, fine.
No,
Because listen, because of the law of conservation of charge, if this thing now has a positive charge because the electrons have moved from it onto this, what charge must this have?
Negative.
Probably negative, right? If the electrons have moved onto it. Oh, yep. So did you see how I was attracted to that too? Because listen, even though this little thing was what charge?
0.
No charge. No charge. There's two ways the object can be charged. So we have how I've charged this. How I've charged this is called charging by contact. That was one of your vocab words too. This is contacting this, right? So it's charging by contact. I can hear it. Does that make sense? You might write that down somewhere. You already have it in your vocab words. But charging by contact is where a charge is transferred when they touch each other, right? Another way that something can be charged is this charging by induction. And so that's what's happening here is even before, and I don't know if you can see this very well on camera, but even before I ever actually touch the tissue paper, the little, did you see that?
Yeah.
It came to it before that. It works better with the balloonie. Let me wear one of these balloonies.
Do it on me.
So, I'm going to rub this on my hair.
No, do it today. No.
So when I rub my hair with it, right, the negative charges from my hair are passing on to the balloon. Okay? So far, so good. So what charge does the balloon have now?
Positive.
No. Charge. Electrons have passed from my hair
So it's a negative.
to my balloon. So the balloon now has a negative charge. Wait, and so by the way, this is charging by contact, right? And so if the balloon has a negative charge, what charge must my hair have now?
Positive.
Positive, which makes it, as you can see, can you
Attract.
in the video see too? Yeah. So my hair's attracting because my hair has a positive charge.
And you can
What
actually-
charge does the wall have?
Neutral.
Neutral, no charge. Okay, so this is charging by induction. Oh, hopefully. Yeah. So what's happening there?
Show me that trick I'm doing Christmas.
So what's happening there? Get out of the way. What's happening there is here's the wall, right? Here's the wall. Both positive, because it's not that every particle that makes up the wall is neutral. It's all scattered about, right? It's neutral on average, but there are both positive and negative charges in it, right? You're good on that. So when I bring the balloon close, and the balloon has a mostly negative charge, when the balloon gets close, it still has some positives, but when the balloon gets close, all the negative charges are like, see ya, right? They're all repelled. So all the electrons go back further into the wall, making the wall have a total charge of, right, because they all moved, so now the wall's charge is
All positive.
positive. Only the positive charge are showing. So now they're attracted. And this is called charging,
By induction.
exactly, charging by induction. You have a phone, some of you, I know you do because you're rich kids, some of you have a phone that charges by induction. With recent advances in modern technology, some phones can charge just by sitting on a little pad, and the same exact thing happens to them. It's quite a bit more complicated than just balloon and wall. But does that kind of make sense? Okay, so now, if I were to remove the charge from this balloon, which I'm going to try, if I was going to remove the charge from the balloon, what would we call that process, do you think? What do you call it when the charge is removed from your phone? No, there's a better prefix. Not uncharging, but
Zapping. Like it just
Not
did.
charging? Not.
Discharge.
discharging. So when the electricity, when the static charge on an object is removed, that's called discharging. So write that down. So when the static charge flows from one thing to another, that's called discharge.
So it's building up, and then whenever it discharges, it does
Yep.
the zapping.
Did you hear it? You almost definitely didn't hear it unless I do it close enough to the mic. But here, charge balloon. Can you hear Mike? Oh, it didn't. I made that noise.
You heard it.
I heard it, but I don't think the microphone actually did. Okay, so when you, Josh, when you're hanging out and Jaden's there in the room and you shuffle across the room with your socky feet and you zap him, right? That's electric discharge, right? You've built up a negative charge. Your little feet are gaining up an electric charge from the floor. Whether it's negative or positive doesn't really matter. And then you go over and you touch Jaden, and then either some of the electrons that were built up on you flow to him, shocking him, or some of the electrons he has in or flow to you because you have a positive charge, shocking you. But it feels the same way, right? This is the exact same thing as lightning. This is something that sometimes blows people's mind if they know that. It's the exact same thing. So what happens is the thundercloud, here represented by yellow balloon, like a thundercloud, rolls over the landscape, here represented by my stupid hair, right? And it builds up a charge. And then because of charging by induction, this is why high objects generally get struck by lightning more than low down objects, is because as the cloud rolls over the landscape, it builds up a charge, and that causes the charge to drive away from the landscape itself. So there's a what we call electric differential here. And so higher up objects, right? You can imagine if the wall were shaped instead like this, obviously the balloon would be more attracted to this little point here. Same thing with lightning. Does that mean that 100% of the time the lightning is going to strike the highest point around? No, but that's where it'll be the most likely to strike, right? Lightning is the exact same thing as the little static shock you give your brother or sister to play with them, right? But it's different in what way? It's just bigger. That's it. That's all it is. The cloud is bigger, the earth is bigger than the balloon in my head, and so therefore the static discharge is also bigger.
So we can make
That's the reason why it go boom.
Yeah.
So we can make lightning.
Yeah. Well, and listen, it is exactly lightning. And listen, just in the same way I was trying to make the microphone hear it go, that is thunder. That is exactly the same thing as thunder. It's just smaller, right? So when you hear the little, right, that's thunder. So there you take that. You can take that home with you and say, Mom, do you want to hear me make thunder? And she'll be like, shut up, I'm trying to tell you I've got a job to do. And then you'll say, okay, I'll try it again. But no, you could still, and that's thunder. That's thunder. So here I've got another thing to show you here. This and I'm gonna have a hard time. So here is yeah, there's no way we're gonna see this on the screen, but this little thing here, you see this little boy?
Yeah.
This is called an electroscope. And so what it is Erlenmeyer flask into which you just put your hand in. Wait, I'll talk to you later. There's a stopper, and the stopper has a metal bar going all the way through it with a little node on the end, and then on the bottom is this little platform with some foil strips hanging down. Okay, and so anytime there's an electrical charge nearby this, that electrical charge, whether it's positive or negative, will be passed on from up here down to these, okay? And so if it's a negative charge, what will this leaf become?
It'll come.
They'll both be negative, and so what will they do?
It'll attract.
No, try again. They'll repel. And if it's a positive charge, what will they both do?
It'll attract.
Nope, try again. They're both positive, they'll still repel. So whether it doesn't tell you whether the charge is positive or negative, it just tells you if there is an electric charge. So right now, nothing's happening. Can you see that nothing's happening? Do you see that? Like I said, there's no way that the computer sees it, or the camera sees it. So is this charged?
Yes.
Oh, jeez.
Okay.
How was that?
Let's find out if this is charged. Do you think we can?
Yes. Just a little bit.
No.
What's rubber?
Yeah.
Explodes.
Let's find out if weights.
Let's find out if this thing's charged. Oh crap, I broke my electroscope. Okay, time to end. Okay, your